Hello, I'm Ethan J. Armis, and this is the Physics 2211 Lab 3 report. This lab was constructed for the purpose of modeling two systems regarding a black hole to find the black hole's mass based on the motion of an orbiting star, then using that mass to determine the initial velocity of a spaceship launching from an orbiting planet such that it does not crash into the planet or the black hole. The important physics principles that we use are Newton's second law, the momentum principle, which can be rewritten as the velocity update formula, as well as the position update formula, the formula for universal gravitation, and the fact that F net can be separated into its components, the sum of the parallel and perpendicular force. As a preview for the results, I calculated the black hole's mass to be 6.68 times 10 to the 33 kilograms, and the spaceship's initial velocity was -3 times 10 to the 7th for the x component, and 2.1 times 10 to the 6th for the y component. In part 1, we created a model of a black hole of unknown mass in an orbiting star. The goal is to find the mass of the black hole. The system is the black hole, and the surroundings are the star, and the star is initially revolving around the black hole at t equals 0, with its motion unique to my Georgia Tech email. The star's mass is 2 times 10 to the 30 kilograms, and delta t is 86,400 seconds, because we are stepping in days, and that's how many seconds there are in a day. In part 2, we created a model of a ship taking off from a planet that is orbiting the black hole in part 1. The goal is to find the initial velocity of the ship so it doesn't crash, but it gets close to the black hole. The system is a spaceship, and the surroundings is the black hole and the planet. The ship is initially launching at t equals 0 from the planet, with forces acting on it from both the planet and the black hole. The ship's mass is 7 times 10 to the 10 kilograms, and the planet's mass is 9 times 10 to the 28 kilograms. The black hole's mass are the results from part 1, delta t equals 1 second, and then below you can see the rest of the initial conditions as part of the code. So in part 1, we found the net force by finding the change in momentum and then dividing it by time. This net force can then be separated into the two components. So we first found the parallel component using p hat and the magnitude of the change in momentum, and plugging that into the definition of the parallel component of force to find the parallel component of force. We then subtract this from the total F net to get the perpendicular force. Using this, what we found, I used a rewritten version of the formula for universal gravitation to solve for the mass of the black hole. The mass of the black hole calculated out to be 6.68 times 10 to the 33 kilograms, and then below you can see the rest of the net force and the parallel and perpendicular components of it. For part 2, I plugged in all the different initial conditions to find the forces acting on both the planet and on the ship. You can see that I have the gravitational, universal gravitational formula used on both, and the net force for both of them, for the planet, would be the force of the black hole on the planet plus the force of the ship on the planet, and then for the ship, it would be the force of the planet on the ship plus the force of the black hole on the ship. Using that, we used the velocity update formula for both the planet and the ship, and then using that, we used the position update formula to iterate over and over again to find the velocity and position of each of them. Since universal gravitation is a non-constant force, we can use the final velocity from the previous iteration on each step. Here, after iterating over and over, using trial and error, I deduced that the initial velocity for the spaceship taking off, in order not to crash but to get close to the black hole, for the x component would be -3 times 10 to the 7, and then for the y component would be 2.1 times 10 to the 6. For what does it mean? It asks, what is the difference between the rate of change of momentum and the net force and its parallel and perpendicular components? Mathematically, they're the same. However, the rate of change of momentum is able to be found through observation by observing its change in velocity over change in time, provided we already have the mass, since we can observe velocity and record time. Net force, however, is more difficult to determine, unless, of course, we know that mathematically it can be found by finding the rate of change of momentum. And then for what if, the what if stipulated that for part 2, instead of just getting close, what if we wanted the ship to orbit the black hole? Through trial and error, I found that the initial velocity for the ship, such that it orbits the black hole, would have to be -1 times 10 to the 6, and then for the x component, and then for the y component, it would be 7 times 10 to the 6 meters per second. Final conclusions, this lab demonstrates the interactions between objects in space and the gravitational forces. Given certain knowns, there's a lot we can determine about these systems and the surroundings by rewriting the different formulas. Also, There's no real source of error since this entire lab was computational. Thank you.